let's look at the energy carried by electromagnetic waves. We know that electromagnetic waves, like any waves, carry energy. A measure of the amount of energy that is stored in the electric field is the electric energy density, so that it's the electric energy divided by the volume. And that electric energy density has this expression 1/2 times permittivity of free space times the electric field squared. Then similarly, a measure of the amount of energy stored in the magnetic field is the magnetic energy density. And magnetic energy density has the value 1 divided by 2 times permeability of free space times the square of the magnetic field. Then the total energy density of an electromagnetic wave in vacuum is the sum of those two energy densities. So we call that just U, and it's 1/2 epsilon naught E squared plus 1/2 over mu naught times magnetic field squared. And when electric fields and magnetic fields travel together to form an electromagnetic wave, the electric fields and the magnetic fields carry the same amount of energy. Then we can say that this value is equal to that value. So when we set them equal to each other and cancel out the 1/2s, we end up with epsilon naught E squared is B squared divided by mu naught. Then if we solve for the electric field by dividing both sides by epsilon naught and taking the square root, we end up with the electric field being 1 over square root of mu naught epsilon naught times B. And we've seen that c, the speed of light, is 1 over square root of mu naught epsilon naught. So then the relationship between the electric field in an electromagnetic wave and its corresponding magnetic field is electric field is the speed of light times the magnetic field. Now, if we're considering the average energy density, so this was the total energy density, then we have to use the RMS value for the electric field, which is 1 over square root of 2 times the maximum value of the electric field, the amplitude of it, and the RMS value for the magnetic field, which again is the amplitude of the magnetic field divided by square root of 2. Then we can talk about the intensity of a wave, of the electromagnetic wave, and we know that intensity S is power divided by area, but power is energy divided by time, so then intensity is energy divided by time times area, and energy is actually energy density times volume, and we still have to divide that by time times area. So energy density was just U from here, and then the volume is the area times, as it were, a height, if you want to think about it that way, to get a volume. So this is a distance. It's the speed of light times time. So this has units of distance times area that gives us a volume. So now we can cancel out TA from top and bottom and end up with the intensity of the wave being C times the total energy density of the wave. So now if we write out the total energy density as this quantity, we end up with the intensity of the wave being equal to 1/2 C epsilon naught E squared plus C divided by 2 mu naught B squared. Since we know that the electric energy density is the same as the magnetic energy density, then we can replace, in this situation, let's say we can replace this quantity by that quantity. So we're adding 2 of 1/2 C epsilon naught E squared, and that means that we just have 1 C epsilon naught E squared as the intensity. But we can do the reverse, where instead of using 1/2 C epsilon naught E squared, we use twice of this, since that quantity and that quantity are the same. So we have the intensity then being either in terms of the electric field or of the magnetic field, and if we know both, then we can just use that more complex equation.